Okay, well, we're 1 minute past the top of the hour, so we're going to go ahead and get things kicked off. So first of all, hello, everyone, and welcome to our second Continuum Town Hall. I'd like to thank you all very much for taking time out of your busy day to join us and to learn about some of the latest developments in the software, as well as to hear about some really interesting research projects. For those of you I haven't met yet, I'm Liz Walls. I'm the lead developer of the software, and with me is Erin Reckley, the product manager of Continuum. We have a number of exciting things on the agenda today, so without further ado, I'll turn it over to Erin to go over what we'll be covering today.
Yeah, thanks, Liz. So we've got a jam-packed session. We've got lots going on. So first, go to the slide. That'd probably be helpful. So first, there's a little database issue that we want everyone to be aware of and how to fix it. Then we'll go over some updates to the new version that's going to be released very, very soon, 1.3.0, including some high-level overviews of two new model features that we've implemented, the elevation component, as well as the valley flow component. And then we've got in our student spotlight, we have Ashlyn Nadeau here with us today, and he's going to share a little bit of his master's thesis, which actually utilized Continuum. So we're really excited to hear more about that. And we've also got a quick update on some work that one of our Continuum contributors has been doing. And then we'll wrap it up with a sneak peek of what's in store for next year and leave some time for an open forum. So first, with this SQL database issue that we came across in the past couple months. Why is this not wanting to work? So the issue came up when Liz and I were going back and forth, working on the same CFM file, but on our own separate machines. And every time that she saved a file and closed it, and then I went to open it, I kept getting this error saying, cannot create a database error message. And so we finally figured out that it was, I had SQL Server database version 2014, whereas she had version 2019. And that was causing some confusion on the database's end, kind of having those mismatched versions. So we've got a fix for it, and it's pretty simple. It's just kind of getting everyone to be using 2019. So you don't have the compatibility issues when you've got multiple people working on different machines trying to access the same CFM file. So you can do this by going to the Continuum website under the Download Continuum software. It pulls up the Dropbox site, and you can download the MSI file that's in there. The SQL Local DB 2019, so it's the 2019 version. So you'll download it. Once you download it, you'll need to uninstall whatever previous version you had. So whether it was 2014 or any other version, you'll want to uninstall that. And then we're going to need to update the link path to the 2019 version. So you do that by going into a command prompt and basically just putting in those three different commands. So you're stopping the link, then you're deleting the old link, and you're creating a new link with the 2019 version. So all of these slides, they're going to be available for reference later on, so you don't have to do it right now. So just be kind of have in the back of your mind, like, hey, I should, whenever you get a chance to get this kind of update to the SQL Server Local DB to version 2019. So with that, Liz is going to again take over and then let us know about some of the new features that are going to be coming up in 1.3.0.
Great, thanks, Erin, for that overview. That was certainly good to figure out. That was driving us a little crazy trying to understand what was going on there, so that was good to resolve. Okay, so let's get into some of the new features in 1.3.0. As Erin mentioned, it's so close to being ready to download and install, but it's not quite there. Expected to be done definitely this week, hopefully today, maybe tomorrow. But nonetheless, let's go over some of the new features that are available in this new version. So there we go. So the first update has to do with the long-term reference tab. So there are a number of new features available on this. So first of all, Error 5 data. So a number of users have made comments like, dang, it does take a long time to download Error 5 data if we're doing it on a daily basis. It'd be really nice if we had the option to download in bigger chunks. So now in version 1.3, users have the option to select either monthly or daily for Era 5 only. Mira 2 is only available in daily. Era 5, though, has the flexibility for different intervals. So you can select now monthly files to download, which is a lot faster. It's about 5 minutes compared to about 15 minutes if you do monthly versus daily. The next update in regards to the long-term reference tab is that there now are a few new optional downloads that you can include when downloading long-term reference data. So if you're downloading either Mira 2 or Era 5, you can now optionally include the 10-meter data. So it will include the 10-meter wind speed and wind direction data. If you check this little checkbox, let me use my laser pointers, there's a little checkbox to include the 10-meter wind speed. And then for Era 5 specifically, there is gust data that is available. And so that is now also an optional download. So if you're downloading Era 5 data, you'll see a little checkbox for the 10-meter gust data. So check that off if you want to include that. And then for Mira 2 data, there's cloud cover data that we use at One Power for certain things. So now that is also available for Mira 2. It's also a little checkbox saying include cloud data. And then I also added in this little dropdown that toggles between local time and UTC-0 or UTC-0 is a little confusing, I found, to use timestamps in local versus UTC-0. So now you have the option to go back and forth. So I think that clears up some of the confusion that caused. And then lastly, there was an error in just labels on the software as well as on some of the exports where the Era 5 temperature data was labeled as 10 meter, but in fact it's 2 meter data. So that's been fixed as well. And then, okay, so that's the long-term reference updates. So again, got Era 5 monthly data, some optional downloads, and some, improvements to the overall GUI. So please do check that out. If you have comments or problems with the new version, don't hesitate to reach out. The next update, though, has to do with the MCP tab. And so this is a bit of a subtlety that maybe some users have not encountered, but at One Power we did. So this has to do with the number of directional bins to include in your MCP. So we have a screenshot of the MCP tab, and in the top right-hand corner, this is where you specify how the MCP should be conducted. Specifically, what I have circled here is the number of wind direction bins to use the MCP. So that tells the software how to divide up the data by wind direction before it does the correlation in the MCP. Meanwhile, we'd have this other number of wind direction bins and an export button down the bottom here. This button at the bottom is to export a tab file. And there's another drop down on that right beside the button for the number of wind direction bins. What that does is it specifies how many wind direction bins to include in the tab file. So those two might not be the same. So at One Power, sometimes we'll use 4 wind direction bins to do the MCP, and then we'll export to a tab file with 16 wind direction bins. So that wasn't working correctly before. That's now worked. Now that is fixed in version 1.3. Okay, so that's MCP. Now moving on to the site suitability tab. So we had a request from Syrian, who I think is on the call. She was, requesting the ability to export the shadow flicker sound maps to CSV. So now when you open the software and go to the site suitability tab, you'll see a little button below the map saying export map. And that simply takes whatever you're displaying on the map there and exports it to a CSV, so you could bring it into ArcGIS, QGIS, whatever it is you want to do with that data. Next is an update to the round robin export. So this is a screenshot of the uncertainty analysis tab on the side where the round robin analysis is done. Before, we only had the option to download essentially the full export, showing the details of all the different round robin wind speed estimate errors. But what we have now is there's a new button just below where it says do round robin. It's just export summary. And so the summary is a very small file. It just has a summary of the overall RMS error for each MET subset size, and it also includes the minimum and maximum error within each MET subset size. So that's been pretty useful for us, again, just to get a summary of the round robin as opposed to all the details. And then next is an issue that were encountered by some of our UK and Australian friends who use a different timestamp format. So in the US, we use month, day, year, but in other countries, they do day, month, year. And so that was causing a bug when importing metadata, when getting reanalysis data. So that has now all been fixed. I just tested that yesterday. So that's all now working. So now if you're in the UK, Australia, wherever, using a different timestamp, you don't have to worry about changing your regional settings anymore. Okay, those are the new features of the software in the GUI sense. Now we're going to switch gears a little bit and talk about two new components that we're adding to the WinFlow model that we're pretty excited about. So the first one is we call or we refer to as the elevation model. So why did we do this? So what was the motivation for it? Well, just intuitively, we know that if there's a big difference in elevation between two sites, that's going to influence the difference in the wind speed, but that wasn't incorporated in the base model of Continuum. And in practice, Aaron and I also observed some pretty significant error at some sites with really significant elevation differences. So it became apparent that we do need to bring this into the model to account for changes in wind speed due to large differences in elevation. So we've introduced a very simple component that we add to the model as I'm showing here. And what this is saying the change in wind speed between two sites due to the elevation is equal to some coefficient multiplied by the difference in elevation. So a very simple linear relationship between change in wind speed and change in elevation. So now we have the original continuum model or the base continuum model, where we have components estimating the change in wind speed due to the change in the upwind and downwind terrain exposure, as well as a change in wind speed due to the upwind and downwind surface roughness. Now with this new elevation model, we are just tacking this on at the end. So it's an additional component that again accounts for changes in wind speed due to changes in the elevation. At sites where there isn't much of an elevation change, this really won't have much of an impact. But again, at really complex sites where there is significant changes in elevation, we're seeing better results when this is included. And this is the model fully expanded out, showing all the various coefficients for the exposure and the roughness models, and now our new elevation component. All right, so let's take a look at some preliminary validations of the elevation model. So what we're showing here on the left-hand side is the RMS, or the MET cross prediction error, for a complex site in New Mexico. And on the right-hand side, it's the results of a round robin analysis at the same site. So what we're seeing for the blue series is the model error when the elevation model was not used. And then the orange line is when the elevation model was implemented. So as you can see, the error was largely reduced at this site. In some cases, it was reduced by about half. Again, this is a very complex site, so we don't expect such a drastic change at a lot of locations, but definitely saw a significant improvement. So we were very encouraged by this, and so we're excited to have this rolled out in version 1.3. Okay, now this is a little finicky. There we go. Okay, the new valley model is the other component that we've added. Okay. There we go. Okay, so what was the motivation for the new valley model? Well, empirically, through observations, we know that the wind speed significantly decreases when you go down into a valley. But we also saw the continuum base model didn't really do a very good job at modeling wind speeds in those types of situations. So we have been working on a new way to model what is happening when you go down into a valley. And so with that, we're introducing this valley component model that is shown here. So this is saying that the change in wind speed when you're in a valley is equal to some coefficient, M valley, multiplied by the difference in the sum of the upwind and down exposure. So what does that mean? Well, first of all, taking a quick step back, so how do we know if we're in a valley? We know if we're in a valley if we have both a negative upwind and downwind exposure as shown in this diagram. So terrain exposure, for those who aren't familiar, is just the average elevation difference between a site and the surrounding terrain, weighted by the inverse distance. So just think of it just as an average elevation difference. So if you have both a negative upwind and a negative downwind, you're in a valley. And so in this model, we're assuming that the change in wind speed when you're in a valley is linearly related to essentially the depth of the valley, or the sum of the up and down exposure. And so what that means is that the deeper the valley is, the lower the wind speed, which makes sense intuitively, and as well as, following empirical data. And keep in mind that this valley model only applies to sites that are in a valley. So if your sites are up on ridge lines, different terrain, then this valley model will have no impact. It's only used to estimate the wind speed change either going into or coming out of a valley. Here we go. Here's the original continuum model with the elevation component added on the end. And then the new model with the valley component, just tack that additional component on the end, and it will take care of estimating the change in wind speed, again, going into or out of the valley. And again, just reiterating, if you have this turned on and you're not in a valley and you don't see any differences in your wind speed estimates, well, that makes sense, because again, this will only impact estimates if you have at least one of the sites in a valley. Okay, so now let's take a look at some preliminary validations. There we go. Okay, so the first site, this is a complex site in New Mexico. This is looking at the results of a round robin analysis. We have the round robin error on the y-axis as a function of the met subset size on the x. And the blue is when you have without the valley flow model, and orange is when it is enabled. So you can see there is a decrease in the error, not as significant, not as maybe impressive as the elevation model, but still going in the right direction. So we were encouraged by that. The second site that we've looked at and done some validations of the valley flow model is a site in Missouri. And so this was interesting. So we have at One Power, we put out LiDAR sites at a lot of the places that we're looking to potentially install wind turbines. And so we had this LiDAR installed in a valley in Missouri. And so what we did was, first of all, we got the LiDAR data and did some long-term wind speed estimate using MCP. And the average at the LiDAR site was 4.19. And we said, okay, so if we have ERA5 data close by, could we use that with the valley flow model to predict what the wind speed is in the valley? And so that's what we did. So first of all, the first bar is showing the modeled wind speed at the LiDAR site down in the valley, but using the base model of Continuum. Again, using ERA5 as an input. So if you use just the base model in this situation, you're largely overestimating the wind speed down the valley by about 24%. But when we turned on the valley and elevation model, the modeled wind speed down in the valley at that LiDAR site was almost the exact same as the actual value. So we were very encouraged by this. The error is 1.2%. We predicted a wind speed of 4.24 down at that site in the valley. So we were encouraged by this, and feel like we're on the right track of capturing the decrease in wind speed when you go down to valley. We're going to explore this site 2 a little bit more. This is, I think, really quite interesting. So just kind of giving you more details on this site and on this validations study that we did. So first of all, just wanted to give you a snapshot of what the elevation looked like at this site in Missouri. Again, this is our site was down in the valley, down in this blue area. We're looking at elevation from 100 to 275 meters. So our LiDAR was down here, but the turbines were going to go on the ridges, right? So on these much higher elevation, 200, so it's a 175-meter difference in elevation. So that's significant. So we ran the model in Continuum using the LiDAR as the input. So a little reverse from what we were just talking about in the other validation. Instead of using ERA5 to model it down at the LiDAR site, in this example, we're using the LiDAR data to model the entire area, so kind of going the other direction. So without the elevation or valley model, the base model really doesn't capture the ridge lines. It's not capturing what we would expect to see in terms of differences in wind speed between a valley and up on this ridge. Now, if we turn on the elevation model, then we start to see, increase in wind speed Here's the scale for the wind speed. It ranges from 4.3 to 5.7. So with the elevation model, now we're seeing an increase in wind speed along these ridges like we would expect to see, but we're still not really seeing that significant the contrast between the wind speed in the valley versus on the ridgeline. So we turn on the valley flow model and okay, this is starting to look a lot more like what we expect. We have now a wind speed on the ridgeline of about 5.7, 5.6 meters per second, which is pretty much in line with what the ERA 5 data was telling us. So that was encouraging. And again, we're really seeing this major decrease in wind speed as you go into the valley. So that's just more of a detailed look at the valley flow model. And again, you can test this out for yourself once 1.3 is available. So with that in mind, I'm just going to quickly show you how to enable these different features. So in 1.3, once you download it, install it, you'll notice a couple of new checkboxes down below the met sites where you import or delete met sites. So if you want to enable elevation model, you just check that box. If you want to enable the valley flow model, you check that box. Really simple to turn it on and off to, again, see the impact of those new features in the flow model. All right, that concludes the overview of the new features, overview of the new wind flow components. We'll talk about those a little bit more a little bit later, but for now, I'm going to turn it over to Erin, who is going to start our first student spotlight.
All right, so yeah, we'll kind of move on to our next section. So with all the stuff that Liz has just been talking about, especially the elevation and the valley flow components, and showing a lot of promise. I mean, you're just seeing those graphics. We're super pumped to be able to roll that out once 1.3 is available. And then also hear from you guys. Is this helping in your projects as well? Are you seeing what you would expect in your wind speeds when you add those components or not? So kind of switching gears a little bit, as Liz mentioned, we have a guest speaker, super excited for. Our guest speaker is Ashlyn Naito. Ashlyn recently finished up his master's degree at Stellenbosch University over in South Africa. So he is joining us remote from over there. When he was working on his thesis, he came across Continuum and was able to use it for the wind modeling portion of his thesis, which he has titled Modeling a Hybrid Wind and Solar Power Plant, a Case Study Within the City of Cape Town. So Ashlyn's previous renewables research includes socioeconomic development and development impacts of wind farms in the Eastern Cape region of South Africa. And he's currently working for the City of Cape Town municipality, where he is leading renewable energy and carbon data efforts. So Ashlyn, thank you so much for taking the time to be with us here today. So if you want to take control of the presentation and then kind of give us a little bit of info about the work that you've been doing.
Okay, thank you for having me. So you guys can see the presentation. Okay, so
yes, we can. Yep.
Yeah, so if you just imagine what I'm trying to do here, basically if you imagine a sea of solar panels and then wind turbines surrounded by those solar panels, that's the general idea. A hybrid utility scale hybrid power plant such as that. So this particular project, I chose a particular place within the city of Cape Town, and I'll show you where. So this is just some policies and guiding strategies that guide the city of Cape Town in its energy endeavors, energy strategies, climate action plans, and so on. So that may be of interest to you later. And then this is just a slide showing you the demand that the plant would have to meet. So city operations, in terms of municipal operations only. So you could see a typical high demand week was about 57 odd megawatts, low demand about 53 odd megawatts. So quite significant, not very high, but it's important to have net zero carbon buildings for policy and net zero carbon by 2050. So where did we build the plant, right? In the study, we had a few options. The yellow land parcels show the options, and they were derived by spatial analysis. we use physical constraints, environmental constraints, and we found these yellow plots. And the one that was chosen was up north. So if you look right at the top, there's a big chunk of yellow there. And if I just zoom in, you can see here it's about 45 odd square kilometers, and it's in a region called Atlantis. So that's north of City of Cape Town, within City of Cape Town boundaries, but north. So that's the study area. And how did the model look like? So the model had three scenarios. You had your wind only, solar only, and then you had the hybrid. For this presentation, we'd only focus on the wind only and the hybrid. And in terms of wind data in South Africa, some people may know or heard of the Wind Atlas for South Africa. It was a project developed by a partnership with the Danish University of Technology and various other research institutions within South Africa and government entities and organizations. And basically, it's a very technical, many years went into that project in developing a sort of high-level overview of wind speeds and wind energy potential for the whole South African country. So you can see this picture on the right showing you energy wind speeds, and basically done using numerical wind modeling, and as well as being ground truthed by 20 odd met masts. And if you look at the picture on the left, the results from the study show you that at every 3 to 5 kilometers across the whole of South Africa, there's what we call virtual met masts. So these virtual met masts are the results of the study, and they give you basically wind speeds across the whole country. So my study area is there. I chose, however many virtual met masts I needed, and that were the closest, so to give me the best results. So that's a bit of interesting wind energy data of South Africa. And so the wind only scenario. So we use that WASA data, Wind Atlas South Africa data, and we imported into Continuum. How did we do that? Well, the WASA gives you lib files, which you just turn into a tab file, which we're all familiar with. You can see at the bottom of the page. That's done through a Python script. And you can see the black dots on the screen. That's obviously the virtual met mass. So you can see I use 3 for this particular study. You could use more, could use less. White is obviously the wind turbines, and then you have your land cover, as we're all familiar with these snapshots, I'm sure, and topography inputs as well. And obviously your power curve. It was a 3 megawatt 3 megawatt turbine. Also, the land cover was also interesting because I know the United States National Land Cover Database has about 20 odd land cover classes, which is what Continuum uses in terms of the displacement and roughness. And in the South African data set has about 72. So the other thing that had to be done is had to classify the 72 South African land cover classes into the US classes, so that the displacement and roughness values fit or similar to some extent, which wasn't too hard. This is just a quick snapshot of the results of the wind farm. You can see producing around 4 to 5 megawatt hours. And then something else that was interesting that I had to do was that obviously to see whether the plant met the demands of the city's operations, we had to have an hourly generation profile. But Continuum only makes an hourly generation profile if you're using time series data. Now, if I go back a few slides, you'll see here there's a little thumbtack that says SAWS towards the south of the picture, right at the bottom. So that stands for South African Weather Services. So that was a met mass by the South African Weather Services that was at a height of 121 meters. So that data we had from 2015 to 2023. So we just used the power law and scale that to a 100-meter hub height, which is what the turbine was at. So we scale that, and then we ran the model again using the SAWS South African Weather Service's MetMass data, right? And we just used the proportions of that for the tab files that we had used. So if, for example, the tab file said, we had 100 megawatt hours in a year, and the source just gave us like, okay, in this hour it was this many percent, in this hour it was this many percent for a whole year. So we just proportioned it like that. So basically that slide just showed you that it showed you when the model was generating energy and how much it was generating energy. But the final analysis just showed that the wind farm alone never produced enough energy to fully support the city. Obviously, you need batteries and so on. But in that particular case, you actually needed grid energy as well, because the batteries were not going to be able to be charged. But if you move to the next slide. So basically this model input slide is showing you now, we just did the wind only. So now this is the hybrid. So how did we do the hybrid scenario modeling? Well, there was just two changes. Firstly, we had to change the layout of the wind turbines because you didn't want the wind turbines too close to the panels in case, they fell over or anything like that. And for maintenance purposes. So we used a formula. It was tip height plus 10%. So that was the buffer around the turbines of the hybrid plant. And then as well as we had to change the land cover. So there's two land cover changes. You'll see at the bottom there in the white block, BOP, balance of plant. So that was I think it's 50,000 square meters that was allocated to balance of plant, which is basically maybe substations, inverters, storage of extra parts and so on. And then obviously the solar panels, which we assumed a height of 1.5 meters. So these solar panels were 700 watt panels. And yeah, so that was the height above ground. And then after modeling that in Continuum, I think before and after, with and without solar panels, the difference in the wind farm output was like 1%. So it was very, very well worth it to install panels. The next slide is just showing you the losses from the wind turbine shading on the panels. And then that was calculated using GIS, ArcGIS, using one of the tools there. So it was about 7%, 6.5 to 7% on average. So definitely well worth installing solar panels underneath wind turbines. The next slide, financials. If you look at the table, this basically it's in South African rands, so maybe a bit hard to follow, but essentially what it's telling you, the first scenario where you only have solar panels, it is cost effective, right? To have this only solar panels to meet city demand. Take into account that any excess energy that comes over and above what the city operations need is sold to city customers. So you do make a profit. And that's what makes the plant financially viable. In the wind scenario, because the plant did not produce enough energy to even sustain batteries, it was not financially viable. But in the hybrid scenario, it was financially viable. And interestingly, the battery needed in the hybrid scenario compared to the solar was smaller. So it does prove that wind, yes, does blow when solar cannot generate. So I think that's a very important fact to remember. So yeah, that's all I have to say. Thank you.
That's great. Thank you, Ashlyn. Really interesting. We'll have more time for questions in a couple. But just one quick thing. I just thought it was so interesting that you thought to change the lane cover where their solar panels are to model the smoother surface roughness over that. So I don't think I've ever heard of anyone do that before. So that was, yeah, that was very cool to see. All right. I think it is on to Erin.
Yeah.
Okay.
So thank you again, Ashlyn, for, yeah, actually, so while Liz is doing that, Ashlyn, I had just a real quick question. What was the total size of the solar and then wind components? So it looked like there were probably 60-ish turbines and you said 3 megawatt. How much solar
Yeah,
versus wind and stuff?
so solar peak was between 4 and 6 gigawatts. It was massive because, almost 45 odd square kilometers. And then the wind peak was, I remember the energy output being around 300,000 megawatt hours, around there. I think capacity factors of wind was around 20 something percent, and capacity factors of the PV was about 18 something percent, which is standard for South Africa. We have wind capacity factors around 30%, quite normal here, and then solar is about 18-20% here.
Okay, so that's pretty typical to kind of what we're seeing over in the US too, in terms of capacity factors for both wind and solar. It's very interesting. That's a big project. It is a large project. Great. Well, again, thank you so much for taking the time and sharing your work. We really appreciate it. So, Ashlyn kind of is using Continuum for real world applications. We also want to give a really quick update on one of our contributors who has been working on some research to enhance the software. So Pablo, he's not able to be on the call today, but he is a field engineer at one power company, and he expressed some interest to both Liz and I in doing some extra research and seeing, can we use machine learning in MCP methods, and that is what he's been working on. So Pablo recognized that some additional variables could potentially help when you are creating the correlations, when you're creating the long-term wind speeds. So we can use machine learning techniques to allow for multiple parameters to be included. And the goal of his study is to determine the benefit of actually using machine learning within MCP. So he's kind of broken this into 3 different phases. He may add more phases, as time goes on. But the first phase, he was doing a small sensitivity analysis with a single data set. So this data set, it had 8 months of measured data, and he used 7 months of that data as the training data set. And then the 1 month that he didn't use, he was using that as his validation. He looked at a bunch of different machine learning algorithms. They're all on the screen. You can read through. The ones in blue, they are actually not machine learning algorithms, but they're the ones that are currently within Continuum that we can use, right now. So he wanted to include those to kind of have a baseline and see, okay, what we're currently doing, how are these new machine learning algorithms comparing to, an orthogonal regression or, method of bins, variance ratio, all those. So in the second phase, he kind of did something very similar. So he just kind of expanded and did more data sets. So we found some longer term data sets, ones that are multi-year, and he was doing that same thing of looking at all those different, or all the same machine learning algorithms and seeing, can we reduce some error statistics using these new methods relative to what we're currently using. So the 3 data sets that he used, they were multi-year. So he used 1 full year for his training data set, and then whatever was left, either 1 year or 2 years as the validation data sets. And then in phase 3, that wants to go. There we go. In phase 3, from phases 1 and 2, he kind of found that the ridge and lasso methods were working pretty well. And those are the ones that he wanted to focus on, as well as the multi-layer perceptron. Try saying that 7 times fast, that's hard. The multi-layer perceptron regression models. So he wants to focus really in on those, and he's been taking some time and implementing that into the MCP module within Continuum. So he on a separate branch so that he can do additional testing and additional studies to kind of have things ready for, if things are doing what we think they're going to do, to be able to implement that in a later version. So that's currently still in progress. He's working through that, and we are very happy that he wants to take this project on, because it is a beast that he is taking on. So we're very, very proud of him for taking this. So a couple kind of graphics. It's not wanting to. There we go. So a couple graphics that he shared with us are some error statistics. He for both phase 1 and 2 for those data sets that he was looking at. So on the left, we've He was looking just at that one short-term data set, that 8-month, using 7 months of training data. And we're looking at the mean absolute error of the hourly wind speed for all of these different algorithms. So the ones that are kind of highlighted in yellow, those are the two that he really wanted to focus in on, the lasso and the ridge. And you can see that it does have a slight reduction, kind of looking across all of the different MAEs of the ones that he tested and is showing. It does have some of the lowest MAEs. We have other error statistics that we also need to look at. So MAE is just one thing, but this is the one that we just wanted to show. And then phase 2, we've got the 3 separate data sets that we're looking at. Again, the ones in yellow that are shaded, those are the lasso and the ridge. So relative to other algorithms that he was looking at, those did seem to be kind of on the lower end of the MAE. So that's kind of what Pablo's been up to. He's continuing his work as well. He's kind of chugging along with it. But I do want to kind of make a little bit of a plug. If you are interested in becoming a Continuum contributor, please, again, check out the website, continuumwin.com/contributors, to see how you can be involved in helping kind of take this software further. And so with that, I am going to toss it back over to Liz, and she's going to let you in on what to expect for next year.
Awesome. Thanks, Erin. Yes, definitely. We have a whole list of open projects. So if you know of any students, or if you are a student who's looking for a master's or even a PhD project, please do check out the list of open projects that you could take on. I think there are some pretty interesting ones on that list. Okay, so the last thing we're going to talk about today is what is in store for 2025. So we have decided that it would be really helpful for a lot of our users, for us, to create a series of lectures that really dive into the Continuum WindFlow model. And so the series, we're calling it Continuum Explained WindFlow Model Lecture Series. And in this lecture series, again, we're really going to dive into the details of all the different components that make up the Continuum model. So the equation that I'm showing here, I showed earlier, and it is the full continuum model, now incorporating our elevation component as well as the valley flow model. So in this series in 2025, we are going to talk about all these different components. So the first couple sessions is going to be all about terrain exposure. So we're going to talk about what is upwind and downwind terrain exposure, what are the different flow types associated with different types of upwind and downwind exposure, and look at this first component of the WindFlow model that looks at how changes in exposure translate into changes in wind speed across a project area. So that'll be the first 2 sessions. Next session after that will be focused on the surface roughness model, which incorporates these 2 terms here. This is looking at changes in the upwind surface roughness and displacement height, as well as changes in the downwind surface roughness and displacement height. So in that session, we'll talk about the log law profile, friction velocity, the stability term, which impacts how sensitive the wind speed is to changes in roughness, and really get into the nitty-gritty of how all that works. Following that, session 4, we will talk more about the elevation and valley component model in more detail. We'll give more examples and really dive into, what the coefficients do, and some real-world examples of those 2 components in action. Session 5 will be all about terrain complexity and how the model coefficients are defined. More specifically, how are the exposure coefficients defined? Not to give things too much away, but these coefficients for the exposure are a function of terrain complexity. So in session 5, we're going to go over how we quantify terrain complexity in Continuum to then define those exposure model coefficients. And then lastly, in the 6th session, we'll go over the machine learning algorithm that is currently in place that is used to find all of these model coefficients that lead to the lowest met cross prediction error. So we'll explore that machine learning algorithm. It's a gradient descent type algorithm. Again, I'll explain how that all works and how all the different coefficients are varied. And so, yeah, so there'll be 6 sessions in 2025. We'll incorporate this into town halls. So we'll also, have updates on the software and student research and Continuum contributors. But this will be happening every couple of months in 2025. So starting in February will be our first one. Again, diving into the exposure component of the model. And then every couple of months we'll have another session. And so 2025 will be, an exciting year. So it'll be lots of fun stuff to explain and maybe some good input from the community. Okay, so that concludes our slides for today. So we have about 10 minutes, so we're going to open it up to any questions or comments, any issues that you all have encountered, or any perhaps requests for changes down the road. So so if there are any questions, feel free to raise your hand, unmute yourself, and we can get the Q&A session going. If there aren't, I have a couple questions for Ashlyn, actually. So see if there are any questions about Continuum. If not, I have a couple questions for Ashlyn. Ashlyn, would you be prepared to share your roughness conversion for South Africa?
I can. I mean, I don't mind. It's basically just binning the South African land cover classes to the US land cover classes, so that it's similar. I don't mind.
Okay.
Yeah.
Great. Well, I think I would love to take a quick look at your land cover key. It's something I've been thinking about for a while, creating kind of a library of these land cover keys for various countries because they have different land cover categories.
Okay.
So let's connect after this and see if we could put together, a little tutorial or a little helpful document for users.
Yeah, there it goes.
Ah, there we go. There we
Yeah,
go.
I
Sorry
was
about
just
that.
wondering, I guess you'll send out an email or something when the new version of a Continuum is available. So we'll know we can
Yes.
go download it and start working with it.
Yeah, I was trying my best to get it done for today, but just not quite there. As a few new
wow.
things. Yeah. But it will be ready. It's just going through some final testing, but I'll certainly post on LinkedIn and on the website when it's available. And I can send a note to the attendees for this town hall when it's ready as well.
Great. Thank
Okay.
you. Looking forward
Of
to it.
course. Great. Thanks, Jack. All right. Did Sarian, did you have a question?
It looks like they were chatting about the land cover stuff and the
Oh, great.
between Ashley. So
Oh,
I think
wonderful. Okay.
they're good.
All right. So Ashley, I had a quick question for you about your research. So the WASA data, the South Africa Wind Atlas, you said that you used a Python script to create the tab files. I'm just curious, how is the data, in what format is the data available? Is it a time series as well that the Wind Atlas provides, or is it an overall distribution?
It's a good question. I don't think I think it's a distribution. It's a lib file, .lib file. I didn't write the Python script to convert it to a tab file. I got that from a professor. But yeah, that's what I understand about it.
Okay, that makes sense. Yeah, because Aaron and I were chatting about it a little bit yesterday, and we were curious. You use the Met Tower data in order to generate the hourly profile to generate the time series. And so we were curious why you couldn't do that with the Wind Atlas data, but it sounds like they don't provide time series. It's a distribution, so that would make sense. Is that
Correct. 100%.
Okay, great. And then other question I had was, you have the plot showing a high demand season and low demand season in South Africa.
Yes.
Just curious, what months do those correspond to?
So the high demand typically would be winter. So it'd be June, July for us when people are running heaters and so on. And then the low demand is probably, I think Christmas is our lowest demand day of the year. But it would be around sort of Jan, Feb when people are still on holiday and things like that. That's typically lower demand for us.
It's interesting. In the US, we sort of have the opposite because Americans love their air conditioning.
Yeah, it's crazy, yeah.
Yeah. Oh, Bauer has a question. Does the valley model seem to have a larger impact on wind speed when using ERA or MIRA? I think that the valley model is going to be independent, really, of that. It's really going to depend on the terrain. So if you're at a site where there's no valley, then the valley flow model is not going to have an impact. It really has to do with what sort of variability you see. The input in terms of the model input, wind speed, wind direction distribution, whether it's ERA 5 or MIRA 2, won't have much of an impact. But maybe your question is more when we were measuring or modeling at that site in Missouri, if we'd used MIRA 2 data, maybe we wouldn't have been able to model the LiDAR wind speed as well. Is that sort of your question?
Yeah, I think I was just thinking like modeled height.
Okay. Yeah, I'm not really sure. We have more investigating to do. We have more research to do. I know that, in general, what we've been seeing is that ERA 5 is typically a better representation of what is actually happening. MIRA 2 can lead you astray in certain situations. But again, yeah, the valley flow model kind of independent of the input. But it would be interesting. Yeah, I think the short answer is we don't really know. More research to be done.
Yeah, that'd be interesting to play around with. Thank you.
Yeah, of course. Okay, any other questions for Ashlyn or questions about the software? Don't think I see any of our Irish friends who had issues with the timestamp issue. I'll have to send them an email letting them know that issue is resolved. Okay. Well, I think we can wrap things up maybe a little bit, a couple minutes early. Again, thanks to everyone taking the time to join us today. I know it's a busy time of year as we're, getting ready for the holidays and we're bringing in the new year. Erin and I are both really excited about 2025 as, we're growing this community and, adding things to the software and getting contributors and students. It's a really exciting time for us. And so again, just wanted to send our thanks out to you for being a part of this and looking forward to 2025.
Yep, absolutely.
Okay.
Thank you, guys.
Oh, there's a question for Ashlyn from Arush.
Okay. So the idea was to maximize the energy the land could generate. So firstly, I just took the biggest solar panel I could get within the software. So I used PVSys to simulate the solar component. It was a 730 watt panel, which is probably the biggest on the market so far. And then in terms of the wind turbine, the number of them, I just that's just heuristic would continue. We need to just put it there, run and see what happens, and then play around, run some more. So that's how I did that. It's not a science, but yeah, it's what I did. The other interesting thing I was thinking with just the modeling of a hybrid plant is if I were to raise the height of the solar panel, say to 10 meters high. So within Continuum, I'd make the displacement value, say 10 or 11 meters, because then you could have your agrivoltaics underneath. From a city point of view, you're trying to maximize your land use, but yeah, this is just
that would be interesting.
Yeah.
One thing I wanted to quickly mention, Ashlyn, the displacement height, typically you don't assume the displacement height is the actual height of the obstacle.
Okay.
Jack, what is it? Usually like a 2/3 of the height, something like that? Is that what we would typically assume?
Yeah, something like that. It varies a little bit, but around that and that neighborhood, sure.
Okay.
So I'd recommend, lowering that to 2/3 of your assumed height.
Okay. Arush, my research it wasn't a financial analysis, more technical, but I can share with you my thesis and then you can read it. It's only It's not a long one, it's 60 odd pages. So yeah, quick.
Well, Ashton, we would love to have a link to that to your thesis on our website.
Sure, no stress.
Yeah, great. So we'll get that posted so that other folks can learn more.
Okay, thanks, Aaron, thanks, Liz.
Of course.
Right. And again, thank you all for
Thanks,
joining
Mr.
us.
Thank you.
Yes, thank you for attending.
Thank you all. Bye.
Yep, thanks.
Great. Saren, you had your hand up still. Did you want to ask something?
Hi, no, I'm fine, thank you. Sorry.
Okay, great. Let me know how the map exports go. If you need it's all working fine, but let me know if you run into any problems.
Thank you. I'm looking forward to see what we can do with that.
Great.
Thank you all. Have a great Christmas and Happy New Year.
Thanks, Jack. You
Thank
as
you,
well.
you too.
And
All right.
we'll be in touch soon, Jack, to set up a call to continue our conversation.
Excellent. Looking forward to it. Y'all take care.
Us as well.
Good.
All right, you
See
too.
ya.
Take care. Bye-bye. All right, well, I'm going to sign off as well. This recording will be available on YouTube in a few days. So thanks again. Take care and have a good rest of your day.